Hello, today we're going to talk about structure 1.4.6. This one is about Avogadro's law. All right, so Avogadro's law states that if you have two gases that have the same volume at the same conditions of pressure and temperature, then they must also have the same number of moles. And so the reverse is true as well. As long as it's at the same pressure and temperature, same number of moles, same volume, like it makes sense. So what that means is if you have a constant pressure, constant temperature, you can treat volume the same way as you're treating moles for your conversions, which is nice. So let's say I have two gases, right? And this is not to scale. So let's say I have gas A and gas B, and this one is 1 liter and this one's 2 liters, and I know that they're at a constant pressure and temperature. I know that I have twice as many moles of B as I do as A. So 2 moles for every 1 mole. It's not exactly a mole, but 2-to-1 ratio of moles. I should probably write that clear. 1-to-2 mole ratio. So Avogadro's law allows us to take some shortcuts when we're doing conversions with volume. So let's say we have something like water decomposing into oxygen gas and hydrogen gas. So let's say that I am making, I do this decomposition reaction, and I make, I don't know, 6.2 liters of oxygen. I know that because of Avogadro's law, I can say that there's a 1-to-2 relationship here for the amount of oxygen produced to the amount of hydrogen produced. There's 1 oxygen for every 2 hydrogens. I can just multiply by 2. 12.4 liters of hydrogen have been produced. It's a lot of gas. But this doesn't work with grams. You can't do this with grams. When you're doing grams, you have to change it to moles first and then use the mole ratio. But because of Avogadro's law, as long as we're at the same constant temperature pressure, I can use volume the same way I use moles. Now here's another example. So let's say 40 cubic centimeters of carbon monoxide reacts with excess oxygen in the following reaction. And they're all gases in this case. What volume of oxygen will be used, and what volume of carbon dioxide is produced if they're all measured at the same temperature and pressure. So we know Avogadro's law is in effect. I have 40 cubic centimeters of carbon monoxide. For every 1 reaction, there's 2 carbon monoxides for 1 oxygen. So I must be using up 20 cubic centimeters of oxygen gas. Same thing if I have 40 cubic centimeters of carbon monoxide. I'm going to use up in every reaction 2 carbon monoxide and produce 2 CO2. And so that's effectively a 1-to-1 ratio. You're going to produce 40 cubic centimeters of carbon dioxide, which is really straightforward. Okay, so this example takes Avogadro's law and applies it to combustion analysis. So we have a gaseous hydrocarbon, it's burned in excess oxygen. The product consists of carbon dioxide and water, measured under the same conditions of temperature and pressure. I can determine the empirical formula of the hydrocarbon because those volumes, those cubic centimeter volumes, I can treat them like moles. So I know that for every 1 carbon, there's 1 CO2. For every 1 water, there's 2 hydrogens. Because we want to focus just on the hydrogen and carbon that make up the hydrocarbon. And so there are 30 carbons for every 60 hydrogens. Divide by the smallest. You get 1 carbon for every 2 hydrogens. So my empirical formula is CH2. Okay, so this links forward to structure 1.5, which is applying Avogadro's law to ideal gases. We're going to get into all of the conditions and like applications of the ideal gas law, when it's useful and it's not useful. The behavior of real gases deviate the most from an ideal gas at very high pressures and very low temperatures. So when the particles are really packed together or they're moving very slowly, they're not going to follow the ideal gas law very well. And so we're going to talk about that in a later section.